In this video, we're going to talk about representing functions as power series. So, certainly we've already seen the formula that the geometric series n equals 0 to infinity of r to the n is equal to 1 minus r if the absolute value of our r is less than 1. Well, there's nothing special about the letter r. We can change it to a letter x and make it look more like a function, and we still get the same true statement. So what we say then is that the function f of x equals 1 over 1 minus x as the power series representation 1 plus x squared plus x cubed and so on, so long as the absolute value of x is less than 1. So what we mean is that if we plug in x equal to 1 into this power series, if we plug in anything between negative 1 and 1 into this power series, we get the same thing as if we would take that same number and plug between negative 1 and 1 and plug it into the function. All right, so why do we care? Well, being able to use power series to express functions is helpful for approximating functions with a polynomial. Again, if we cut this off, we would have a polynomial approximation to 1 over 1 minus x, which may not seem very important, but if you want to figure out things like sine of a value, well, there's no sine function built into your calculator or built into your computer, because all your computer can do is add, essentially. It flips digits around, zeros and ones, makes binary digits, flip those around. It understands how to do arithmetic very, very well, but doing sine, not so much. So having a really, really good approximation to a function using a polynomial is important to be able to do arithmetic computations on functions that aren't polynomials. It's also useful in finding antiderivatives of functions that we haven't been able to do antiderivatives for. For example, like e to the x squared does not have an elementary antiderivative, but we can antidifferentiate it if we use a power series representation. Also, there's a method of solving differential equations involving power series, and it's very helpful in being able to solve those types of differential equations. Okay, so we have lots of different applications for power series, which is why we study them. All right, so let's first do an example of finding a power series representation for another function. Let's look at g of x equals 5 over 7 minus x, and then also find its interval of convergence. Well, we're going to use the power series representation that we already found before for the geometric series, 1 over 1 minus x. This has a similar form to that. So there's a couple of ways we can actually get a power series representation, depending on where we might want to center this thing. All right, so let's talk about two of them. Let's start with our function g of x equals 5 over 7 minus x. I want to make this look like 1 over 1 minus something. So something has been plugged in for the x. Okay, that's our goal. Well, the way to get a 1 here rather than a 7 is to factor a 7 out. If I factor a 7 out of the denominator, it leaves with an x over 7 here. I can also pull the 5 out of the top, so I get 5/7 times 1 over 1 minus something. That something happens to be x over 7. So I plug in the x over 7 in for x into the power series representation. So now I have a power series representation for g of x that is 5/7 times the series n equals 0 to infinity of x over 7 to the nth power. And if I want to be fancy, I can bring the 5/7 in and rearrange some exponents. That last step isn't necessary, but just to see that we really do have a series of some terms. All right. We know that the power series representation for 1 over 1 minus x is valid if absolute value of x is less than 1. Well, in this power series representation, we've plugged in x over 7 for x. So this power series representation will work for 5 over 7 minus x so long as x over 7 is less than 1. Or if we move the 7 to the other side, we get that the absolute value of x has to be less than 7. So that tells us that this series will converge for any x's between negative 7 and 7. And again, we just used the fact that we could plug in x over 7 for x into the condition that tells us when this geometric series also converges. All right, let's think about another way we could have done a power series representation. We could also write this as 1 minus something just by simply rearranging some things in the denominator. I can think of 7 as 1 plus 6, and then we can factor out a negative sign. So we get 1 minus the quantity x minus 6, and pull the 5 out in front. this now has the form 1 over 1 minus something. So I can get a power series representation by plugging in x minus 6 for x. And again, I could move the 5 inside, but it's not really necessary. But here's a power series representation for the function. It will converge again. We've replaced the x with x minus 6. So it will converge so long as absolute value of x minus 6 is less than 1. So now in this case, the radius of convergence is only 1 versus 7 like it was in the previous case. And the interval of convergence here is going to, well, we go 1 unit below and above 6, so we get an interval from 5 to 7. So what are the reasons why we might want to use one over another? Well, this one should be a little bit faster approximation at, say, 6.5 than the other one. The closer you get to the endpoints, the longer it'll take to converge. However, this one will not converge near 0 at all, so you would need to use the other one. So you got different reasons for using different representations. All right, so we've just done in this example, we just did some substitution to find new functions, new power series representations from old ones. Other techniques are using integration or differentiation to do that. And we can integrate and differentiate power series just like what we do for polynomials. Namely, we'll use the power rule. So, if we have f of x is the sum from 0 to infinity of c sub n x minus a to the n, and we have a non-zero radius of convergence. We need actually some x values at which we can take derivatives. Remember, for derivatives, we have to have two-sided limits coming in. So we need to make sure this converges for an actual interval, not just at a single point. Well, then we can take the derivative using the power rule. We would bring the n down in front, decrease the power by 1. Here, remember again, if we put in 0, we get just c sub 0, we get a constant. The derivative of a constant is 0, which is why this series starts at 1 rather than 0. Integrating, we can also use the power rule. We would increase the exponent by 1 and decrease the divide by the new exponent. It turns out that when we do a derivative or an integral, you get the exact same radius of convergence as the original. So let's see if we can find a power series representation for 1 over 1 plus x quantity squared. So first, we'll start with a power series representation for 1 over 1 plus x. 1 over 1 plus x is the same thing as 1 over 1 minus a negative x. This looks like our geometric series, except for we have negative x plugged in for x. So we'll get the sum n equals 0 to infinity of negative x raised to the nth power, or negative 1 to the n times x to the n. And this converges so long as absolute value of x is less than 1, just like the original, because when I do the absolute value of negative x, that's the same thing as absolute value of x. Alright, so we're going to get a power series representation for 1 over 1 plus x quantity squared. Well, we note that if I take the derivative of f of x, I get the negative of 1 over 1 plus x squared, which is the negative of g of x. So, if I differentiate both sides, up here, we get negative 1 over 1 plus x squared is the sum from n equals 1 to infinity, again starting at 1 because the constant term fell off, negative 1 to the n times x minus, or x times, nx to the n minus 1. So if I multiply both sides by negative 1, I get a power series representation for g of x that looks like negative 1 to the n plus 1, nx to the n minus 1. All right. We know the radius of convergence. Well, we know when the original power series converge. We don't know anything yet about the derivative. So we need the following theorem. If we have a power series that has a non-zero radius of convergence, then that power series, that function is differentiable on the interval a minus r to a plus r, but maybe not at the endpoints. And the power series representations of the derivative and the integral have the exact same radius of convergence. We saw that the radius of convergence for f of x in this example was 1, So the radius of convergence for g of x is also 1. However, what this theorem does not tell us is what happens at the endpoints. Okay? We don't know if we know where f of x converges. In fact, it doesn't converge at either endpoint. But this theorem doesn't tell us anything about whether or not g of x converges at either endpoint. Okay? So the theorem says that the radius of convergence stays the same, but endpoint convergence might change. So we need to check the endpoints of the power series representation for g of x that we found. So we plug in 1 and we plug in negative 1. Certainly, if I plug in negative 1, these will going to be the same sign all the time. We're just going to get 1. So we just get the series of n, which certainly diverges. Likewise, if we put in 1, we'll get an alternating series of n, which also diverges because that's just going to get bigger and bigger. Just some of them will be negative and some of them will be positive. So our interval of convergence for the power series representation for g of x is just negative 1 to 1. Well, let's see if we can do a power series representation for natural log of 1 plus x. Well, we already saw what the power series representation for 1 over 1 plus x was in the previous example. And we note that if we take we find the antiderivative of f of x, we get h of x plus a constant. So we can find a power series representation for h of x simply by integrating the power series for f. So again, the nice thing about the theorem says is that we can integrate term by term. So do an antiderivative here. We'll add 1 to the exponent, divide by the new exponent. So we get x to the n plus 1 over n plus 1. Still starts at 0. And then we have an arbitrary constant. Now in this case, the constant's not all that arbitrary because we can figure out what c has to be. When we put in 0 for x here, we get natural log of 1, which is 0. When we put in 0 for x here, all of these terms are going to go away. Your first term here is x to the first. So this is going to be 0 when we plug in 0 for x. So we'll get 0 has to be c. So our power series representation for h of x will be the sum n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. The original function, f of x, had a radius of convergence of 1, which means that the radius of convergence for h of x will also be 1. However, we still have to check the endpoints. When we put in negative 1 for x, we get negative 1 to the n times negative 1 to the n plus 1 over n plus 1. Negative 1 to the n and negative 1 to the n plus 1 always have opposite signs. One of them will be positive and the other one will be negative. So when you multiply together, you're always going to get negative 1 no matter what. And that series diverges. It's the opposite of the harmonic series. When x equals 1, however, we get 1 to the n plus 1, which is just 1. So we get the series n equals 0 to infinity of negative 1 to the n over n plus 1. That one should be looking very, very familiar to you about why this series converges. So that tells us now that the interval of convergence for h of x is the half open interval, negative 1 to 1. Negative 1 is not included, 1 is included.